Okay, now we're going to talk about polar coordinates. So the first lesson we're going to do today is on basic polar coordinates. So polar coordinates have two parts, just like rectangular have x and y. You have r and theta. So in this graph right here, I have two lines, and then you can see theta is the angle and r is the distance from the origin. So if this is the origin, r is the distance, and that's defined as r comma theta. So it's important to know how to convert from rectangular, so that's your xy coordinates, to polar, and from polar back to rectangular. So these four formulas are what you need to know. So if you're given rectangular coordinates, you can use your y and x points to find theta and r, so that will be finding your angle and your distance. If you're given polar coordinates, you can solve for x and y using r cosine theta and r sine theta. And the reason why is because if you drew out this graph and defined all your points, this value here is your x value and this is your y. So tan theta is y over x, and then r squared is x squared plus y squared. That's like the Pythagorean theorem. So that's where those formulas come from. You have your example one is up here, and that says to convert to rectangular, and you're given 4 comma pi over 6. So you're given polar coordinates. What you want to do is you want to use these two formulas. You want to solve for x and y. So you get x equals 4 cosine pi over 6, which simplifies to 2 root 3, and y equals 4 sine pi over 6, which simplifies to y equals 2. So your final rectangular point will be 2 root 3 comma 2. If you're converting back to polar, like in example 2, you can see I've given you negative 1 comma 1. So you want to use r squared equals x squared plus y squared, and tan theta equals y over x. So if you're solving for r, you put in x and y, and you get r equals root 2. And if you're solving for tan of theta, you get negative 1. And if you found tan of negative 1, that will come out to 3 pi over 4. So your polar coordinate that would look like this is root 2 comma 3 pi over 4. The last thing we're going to talk about is derivatives of polar curves. We'll get to polar curves in a later video, but all you need to know is that if you can find r and theta, just like you find dy dx, you can find dr d theta. So dr is the change in radius, and d theta is your change in angle. So when dr d theta is positive, that means your point is moving away from the origin, or your change is positive, so all of your values are increasing. If your dr d theta is negative, then your point is moving towards the origin, so all of your values are decreasing. Okay. All right, now we're going to talk about tangent lines. So if you're ever given an equation like this one, r equals f of theta, you have to convert it into our rectangular form. So x equals r cosine theta and y equals r sine theta. And in calculus, we always need to know how to find the derivative. So you can find dx d theta and dy d theta using product rule or whatever derivative rules you want to use. And if you're trying to find dy dx, so that's your derivative or your slope, you want to find dy dx equals dy d theta over dx d theta. And since you have d theta on both sides, you can get rid of that. And so your dy dx will have theta values in it. Let's talk about vertical and horizontal tangent lines. So if you found your dy d theta and your dx d theta, and one of them equals 0 at some amount of points, at those points, which you'll see on graphs, you'll see a horizontal tangent. If dx d theta equals 0 at some points, then you'll have a vertical tangent. So in this example over here, I put down to find the horizontal and vertical tangents at r on the graph. R equals 2 times 1 minus cosine theta. So the first thing you want to do is convert into x's and y's. So I started in with y. So I said since y equals r sine theta, I substituted that in, so it's y equals 2 times 1 minus cosine theta times sine theta. If you found the derivative and simplified, you'd get dy d theta equals negative 2 times 2 cosine theta plus 1 times cosine theta minus 1. And if you set dy d theta equal to 0 to find your horizontal tangents, you'll see that you have horizontal tangents at theta equals 2 pi over 3, 4 pi over 3, and 0. The same way goes for finding your dx d theta. So you want to substitute r in for x equals r cosine theta, and write x equals 2 times 1 minus cosine theta times cosine theta. If you found the derivative and simplified, you get dx d theta equals negative 2 sine theta plus 4 cosine theta sine theta. And if you set dx d theta equal to 0, you'd have vertical tangents at theta equals 0, pi over 3, and 5 pi over 3. So if you want to go even further and find dy dx, all you have to do is write dy d theta over dx d theta. So you get dy dx equals -2 times 2 cosine theta plus 1 times cosine theta minus 1 over -2 sine theta plus 4 cosine theta sine theta. I'm not doing this slow. No way. We're done. Now we're going to talk about area in polar coordinates. So the idea is to use infinitely small sectors to define area. So as you can see, I wrote out the formula. It has to be an integral since you're using infinitely small sectors. So it's 1/2 times the area from A to B times r squared d theta. So your r would be whatever equation they've given you for the graph. And to illustrate this, I wrote it out to have a random polar curve, and it's using the sectors from A to B, and it'll find the area in between. So to find where the graphs, these are the three things you need to know. So to find where the graph starts, you plug in 0 for theta, so that'll give you the first point. To find your bounds, you want to set r equal to 0, so whatever your r equation is, put that equal to 0 and solve for theta. This can be done on a graphing calculator. And then to find your points of intersection, you set the two equations equal to each other and solve for theta. And this can also be done on a graphing calculator. That's it.
Yeet.
Okay. All right, now we're going to do some examples of the three things we talked about before. The first example says to find the area of one petal of this rose curve, r equals 3 cosine 3 theta. So I've written down the area formula up here without the bounds, so it just says a and b. And it's 3 cosine 3 theta squared, and that's from the area formula. So if you graph this on a graphing calculator, or you've plugged in 0 for theta, which is what we've done before, you would find that a is negative pi over 6 and b is pi over 6. And then as you can see the arrows, a is where the graph starts, and then b is where it hits the x-axis, or the origin for the first time. So that's the area of one petal, and that's all they're asking for. So it's a equals 1/2 negative pi over 6 to pi over 6 time, with the integral inside being 3 cosine 3 theta squared d theta, and that would equal 3 pi over 4. Our second example is to find the area of the region lying in between the inner and outer loops of r equals 1 minus 2 sine theta, and that's a loop limison on the side. So to find the inner loop, you would do a equals 1/2 from a to b times, or with the integral inside being 1 minus 2 sine theta squared d theta. If you were to graph this, you would find that the area of the loop is covered when a equals pi over 6 and b equals 5 pi over 6. And that would just be from finding, you would want to find where the graph touches 0. And so that will give you the inner loop. The outer loop is just what's remaining. So a equals 1/2 a to b, 1 minus 2 sine theta squared d theta. And you would want to go from pi over 6, since that's that point right there, all the way around to 13 pi over 6. That's where the graph ends. That would cover all of the orange area, including the inner loop. And so to find the area between, you want to do the outer minus the inner. So if you did the math on a graphing calculator, you get 8.881 minus 0.544 equals 8.337, and that's about the area between the two loops. Our third example says to find the area of the region between r equals negative 6 cosine theta and r equals 2 minus 2 cosine theta. So this one covers how to find points of intersection. So to find the intersection points, before I get to that, we want to make sure we're only working with the top half because this graph is symmetrical, so we don't need to worry about doing both points of intersection. So to find the point of intersection, you would do negative 6 cosine theta equals 2 minus 2 cosine theta. That will give you an intersection point at 2 pi over 3. So since the circle graph hits a point at pi over 2, you want to go from 1/2 times pi over 2 to 2 pi over 3, so that's our intersection, of negative 6 cosine theta squared d theta. And then to find the remaining orange area inside the cardioid, you would want to go a equals 1/2 2 pi over 3, so that's the intersection point to pi, and that is where the graph touches the x-axis, times 2 minus 2 cosine theta squared d theta, and that is the formula for the cardioid. And if you did the math on a graphing calculator, you would, and since you have to do 2 times this because you're finding the area of
the entire region, it would be 2 times 0.815, so that's from the first one, plus 7.039 from here. That'll give you 15.708, which is around 5 pi. Okay, done.